Okay, so yesterday we looked at some of the devices we use. We looked at the energy balance equation. Sorry. Looked at the energy balance equation and we looked at some of the terms that will cancel out depending on the particular equipment or the particular units we are considering. So we considered nozzles, diffusers, compressors, and we'll continue from throttling valves today. And then we'll end with heat exchangers and boilers, and then we'll move on to the next topic. So we are almost done with this slide. So when we talk about throttling valves, these are devices that are used to restrict the flow of our material. And when we restrict the flow of the material, what's going to happen is that there's going to be a drop in the pressure that the material is coming with. So if maybe the material was coming in at maybe 1 bar, we can use a throttling valve to drop the pressure to maybe 0.5 bar by just blocking that material as it's flowing. So unlike turbines, throttling valves are able to produce a pressure drop without involving any work. So remember that for turbines, there's some work that is going to be involved for the pressure to change. And then the pressure drop in the fluid is often accompanied by a large drop in temperature. So this is one thing to note about the throttling valves, that when the pressure of the fluid drops, there's usually a change in temperature as well. And so for that reason, throttling devices are commonly used in refrigeration and air conditioning applications, in places where we work with temperature changing. Okay, so these are examples of valves. The first valve we have here is called a butterfly valve. And then the second valve is called a ball valve. So there are different kinds of valves. But then these are just some examples. So you realize that as the fluid is flowing through the pipe, this valve here can open and close and can allow more or less liquid to flow through. So it's offering some kind of resistance to the flow of the liquid. And in that case, it can reduce the pressure at which the liquid will be flowing. And it can also cause there to be a change in the temperature of the liquid or of our fluid. Okay. So this was a general energy balance equation. For the throttling valve, we are going to also assume that the net change in heat energy is approximately zero. So there's not a significant change in the heat energy of our system. And we are also working with the assumption that our potential energy is going to zero because there's not going to be a significant change in the height or the elevation. And the same thing for the kinetic energy. We assume that the change is almost equal to zero. So there's not a significant change in the kinetic energy of our system. And then there's no shaft work being done. You don't have any rotation or moving mechanical parts to introduce some kind of shaft work. So if we cancel out all those terms from our general equation, we'll just be left with the enthalpy term. That means that for throttling valves, the enthalpy coming in would be equal to the enthalpy moving out. So the enthalpy before it meets the valve would be equal to the enthalpy after it leaves the valve. Now, we know that enthalpy is a state function and it depends on temperature and it depends on pressure. So the enthalpy that is coming in at a certain temperature and pressure. And when it's moving out, it will move out at a certain temperature and pressure. But at the end of the day, whatever temperature and pressure we're working with, the enthalpies have to be the same. So we are saying here that that change in pressure is going to lead to a change in temperature because we said for the throttling valve, there will be a change in the pressure. And so that change in pressure is going to cause a change in temperature. But at the end of the day, we are going to have the same enthalpy. Okay. When we deal with ideal gases, however, we are working with the idea that the temperature is going to remain constant. So this is because, with ideal gases, we can drop the pressure, but we are not going to see a significant effect of the pressure on the enthalpy as compared to temperature. So when we are dealing with ideal gases, the enthalpy is more defined when it comes to temperature. Remember our ideal gas table. Realize that for the ideal gas tables, the properties are given at certain temperatures, not at pressures. Because the effects of pressure on enthalpy for ideal gases can easily be neglected. So we work with temperature more. And if we are saying that the enthalpy before and after have to be the same, and we are not considering pressure, we're only considering temperature, then it means for the ideal gas, the temperature before and after has to be the same in order for the enthalpy before and after to be the same. Please, does that make sense? Please, are we fine with that? Okay, sure. So we have an example here. Sorry. We have an example here. And the example is refrigerant 134A enters the capillary tube of a refrigerator as a saturated liquid at 0.8 megapascal, and it is throttled to a pressure of 0.12 megapascal. Determine the quality of the refrigerant at the final state and the temperature drop during this process. So now let's analyze the question very well. We are saying that we have a certain fluid, that's refrigerant 134A. It enters the tube of a refrigerator as saturated liquid. So it's coming in as saturated at 0.8 megapascal. So we can determine the enthalpy at that condition, the enthalpy at 0.8 megapascal when it is saturated liquid. And we can also get the temperature there. So if we go to our thermodynamic tables, so for refrigerant 134A, so that's, yes, that's this table. And then the temperature we're told was, sorry, the pressure was 0.8 megapascal. So that's 800 kilopascal. So we can easily read the corresponding temperature at that point. That's 31.31 degrees Celsius. And then we can also read the enthalpy. So let me just highlight this rule so that we don't have to go back and forth. So we can also read the enthalpy, right, when it is saturated. So the question told us that it's coming in as a saturated liquid. And remember we said for saturated liquid, we are going to read HF. So I'm going to read the HF value at the 800 kilopascal, and that's 95.47 kilojoule per kilogram. So that's going to be the enthalpy of what is coming to the valve, right? And that enthalpy has to be the same as what is coming out. So now it's been throttled to a pressure of 0.12 megapascal, but it should have that same enthalpy we found. So at 0.12 megapascal, we can look at the enthalpy we have, look at the enthalpies on the table. If our enthalpy is within a reasonable range, we can tell that, okay, it's going to be maybe liquid vapor mixture, right? So that's what we need to determine the quality of the refrigerant. And then at the end of the day, because we've been able to also determine the temperature at 0.1 megapascal, we'll now be able to find a change in temperature. So let's take it one by one. We said at 0.8 megapascal, which is 800 kilopascal, the temperature of the saturated refrigerant was 31.31 degrees Celsius. So I think we are fine with that part because you read that one from the table. And then the enthalpy of the saturated liquid, emphasis on saturated liquid, because the question told us it's a saturated liquid, will be 95.47 kilojoule per kilogram. So we read HF because it was a saturated liquid. Now we also know that the enthalpy is not going to change. So what is coming in will be equal to the enthalpy coming out. So that's all going to be 95.47 kilojoule per kilogram. At the new pressure of 0.12 megapascal or 120 kilopascal, and at that same enthalpy, we want to tell the quality of this. Oh, sorry, it wasn't supposed to be steam. It was supposed to be of the refrigerant. Remember we said for the quality of the refrigerant, we can use this expression, right? Or we can simplify the Ag minus HF in the brackets here to HFG. So the H here is that enthalpy we found that is not going to change. But then the HF and the HFG are what we are going to read at the new pressure, because we want to find the quality at that new pressure. So we are going to read HF and HFG at that new pressure. So if we should come to our thermodynamic table, the refrigerant table, we are looking at 120 kilopascal. So that's this row here, right? And we can easily pick the HF value, and we can easily pick the HFG value as well, right? So if we just pick those values and we put it into our expression over here and make X the subject, we can easily determine the quality. And the question also told us that we should determine the pressure drop. Now, because the refrigerant is going to be a liquid vapor mixture, we can tell that from the quality. It's a liquid vapor mixture. It's saturated at 0.1 megapascal. So we can just read the saturation temperature. So if we go back to our table, the saturation temperature at that point was minus 22.32 degrees Celsius. So we can now determine the temperature drop. So that's a change in the temperature. So we can do the final temperature minus the initial temperature. Then we'll get the value of minus 53.63. So it means that the temperature will drop by a magnitude of 53.63 degrees Celsius. Please, are we okay? Is that fine? Okay, then I'll go on. Now we can also look at heat exchangers. So as the name implies, a heat exchanger is just a device that would have two streams passing through it, and then they are going to exchange heat between each other. So there's one stream that will be hotter than the other stream, and it's going to lose heat to that other stream. So one of the streams will need to be cooled, and then the energy is exchanged in the form of heat without the streams actually mixing or coming into direct contact with each other. So I can have liquid A flowing through a pipe, liquid B flowing through a pipe as well. Liquid A is hotter than liquid B. So the two liquids, I'm not mixing them. But just because the pipes are close to each other, the heat from liquid A can easily get to liquid B to heat it up. So that's what we mean when we're talking about heat exchangers. So we have two fluids, or we have a number of fluids moving through the system. There's a stream that is hotter than another stream, and the heat can be transferred to that other stream. So for the heat exchangers, we can classify them as either counter current or co-current. When we say a heat exchanger is counter current, this is what we are trying to say. So let's say this is our heat exchanger, and then this is our hot stream. So it comes in and then it comes out. Now, let's say our cold stream, the stream that is colder, so I represent that with blue, also comes in this direction, and then it comes out in this direction. Because they are moving in the same direction, we call that co-current. Now, if we had a situation where we rather had maybe our exchanger, we had the hot stream coming in this way and then coming out that way. And then we had our cold stream coming in this way instead and coming out this way. Then we have what we call counter currents. So they are moving in opposite directions, right? So these are some of the classifications. There are other ones. There's cross flow and other things, right? So the types of heat exchangers we have, you can have a shell and tube heat exchanger. You can have a plate type heat exchanger. They're just different types of heat exchangers based on how they are designed, their number of tubes, etc. Okay, there's a question. Someone is asking which value gives a good quality? Is it when it is close to one or close to zero? So the thing about the quality is we said when it is closer to one, then we are having more of a vapor. When it is closer to zero, then we are having more of a liquid. So it actually depends on what you are looking for in order for you to define it as good. If your system is such that you desire to have more vapor, then you want a quality close to one. But if your system is such that you don't want vapor, you rather desire more liquid, then it's better for your quality to be closer to zero. But then when it is in between zero and one, it means that it's a mixture of liquid and vapor. Is that okay? Okay. So we can also define heat exchangers as radiant or as conventional. Radiant working with radiation heat transfer. So we can have two pipes and then the heat is just going to move by radiation between the two of them. Or conventional where we have some fluid in between them. So it would move through the pipe, through the fluid to the other pipe, something of that sort. So we can have radiant and we can have conventional heat exchangers. Okay. So think we can move on. So this is how a heat exchanger looks like. So as we said, we can have the blue stream here is going to be the cold stream, and then the red stream is going to be a hot stream. Realize that as the two of them are moving, there's heat that's going to be exchanged between them, right? And we can also see something of that sort here. So here we have our fluid coming in from the base here, and it's cold. As it moves through the heat exchanger, it comes out hot. And we have another stream coming in here. So this one is coming in hot. And as it moves to the heat exchanger, it will come out cold. So we have two different streams, and one is hotter than the other. Heat is going to be transferred from the hot stream to the cold stream. Okay. So when we want to do the analysis for a heat exchanger, we'll start once again with a general energy balance. Now, for this, we are also going to assume that, or in fact, there's no shaft work. We don't have any rotating, moving mechanical parts that are going to introduce any kind of shaft work. So shaft work goes to zero. We're also assuming that there is no significant change in kinetic energy of a material. So that term can also go to zero. There's also no significant change in the potential energy. So the elevation is not, we don't have such a significant difference in the elevation. So that also goes to zero. And someone might wonder why we are saying that Q should be equal to zero when we are dealing with a heat exchanger. What we are saying by this is that the amount of heat in the system is not going to increase or decrease. We are just exchanging it. So if maybe I give you 30 CDs, the amount of money we both have in total is not going to change. It's just that there has been transfer from me to you. So if we consider the heat exchanger as the entire system, the Q is going to be approximately equal to zero, unless we have some heat coming in from the surrounding or going to the surrounding. But here we are assuming that the heat is just being transferred between the fluids. So the net heat in the entire system, the net heat change in the entire system is approximately zero. So if we do that, we cancel out Q. If we do that, we cancel out Q, we cancel out our shaft work. We can take out our kinetic energy and potential energy terms. All that we are going to be left with is going to be our enthalpy terms for the inlet and then the outlet. And remember, we said earlier that when we have more than one stream, right, we consider the enthalpy flow for all those streams. So we have two inlet streams because we are dealing with two flows. We have two inlet streams. We have two outlet streams, right? We are dealing with two fluids. So each fluid would have a place it's coming in from and a place it's coming out from. So two inlets, two outlets. When we have such a situation, then it means that we have to find the enthalpy flow coming in. So that's going to be the sum of the two inlet enthalpy flows. Then the enthalpy flow coming out. So that's going to be the sum of the two outlet enthalpy flows. So we can see that here we have, for the diagram on the right, we have fluid A and we have fluid B. So fluid A has its inlet and its outlet. Fluid B has its inlet and its outlet. So for the enthalpy coming in, this part here is going to be the mass flow of A times its enthalpy of what is coming in. Then the mass flow of B times its enthalpy of what is coming in. And we are saying that because this is going to be balanced, after we cancel out our terms, the mass flow and the enthalpy coming out, right? If we sum everything, should be equal to what we summed for what was coming in. So mass flow of A coming in times its enthalpy plus mass flow of B coming in times its enthalpy should be equal to the mass flow of A coming out times its enthalpy plus the mass flow of B coming out times its enthalpy flow or times its enthalpy, right? And one other thing to note is that the mass flow is not going to change. So whatever mass flow A had is going to come in and out with that. Whatever mass flow B had is going to come in and out with that. So we also proved that yesterday, right? So we are saying here that MA in will be equal to MA out. So we can just represent it with MA. And then MB in will be equal to MB out. So we can just represent that with MB. So if I change all the MA in and MA out to MA, and then the MB in and MB out to MB, I can group like terms. So I can send everything with MA to one side, everything with MB to one side. I can factorize and I'll end up with the last expression we have here. So this is the expression we use when we are dealing with heat exchangers. Heat exchangers while we work with these assumptions that we were working with. Okay, are we fine up to this point? Okay, sure. So we have an example here. So once again, refrigerant 134A, but this time we are cooling it by water in a condenser. So we see our two fluids. We have refrigerant 134A and we have water. And we are being told that water is being used to cool it. So it means that water is going to be colder than the refrigerant. So the refrigerant enters the condenser with a mass flow rate of 6 kilogram per minute. So they give us the mass flow rate of the refrigerant at 1 megapascal and 70 degrees Celsius. And it's going to leave at 35 degrees Celsius. The cooling water would enter at 300 kPa and 15 degrees Celsius. And it's going to leave at 25 degrees Celsius. So we're told to neglect any pressure drops. It means that the pressures are not going to change as the fluid is moving through the system. So we are supposed to determine the mass flow rate of the cooling water and then the heat transfer rate from the refrigerant to the water. So now if we draw a diagram for it, so we can have this block to represent our heat exchanger. Our refrigerant is coming in. We're told it was having a mass flow of 6 kilogram per minute. When it's coming out, that mass flow is not going to change. So it's the same mass flow in and out. Then the pressure as well. We're told that the pressure, there's not going to be a pressure drop. So 1 megapascal for what was coming in, 1 megapascal for what was coming out. And we're given the temperature at the point when it was coming in and then the temperature when it was coming out. For the cooling water, we have the cooling water also coming in and then the cooling water coming out. We don't know the mass flow of the cooling water. Okay, sorry. We don't know the mass flow, but then we know the pressure. So the pressure of what is coming in will be equal to the pressure of what is coming out. And we're given the temperature of the inlet and then the outlet. So what we can do is that we can do our energy balance, cancel out the terms, and we end up with this expression that we concluded on previously. Now we can say that we replace A with R for the refrigerant, and B with W for the water. So we'll have the mass flow of the refrigerant times its enthalpy out minus its enthalpy in being equal to the mass flow of water times its enthalpy in minus its enthalpy out. So these values, we can read them from the tables. We can read that of the refrigerant from the table because we're given the temperature and pressure. We're giving here the temperature and the pressure, right? So I want you guys to try that out. You read the enthalpy at 1 megapascal and 70 degrees Celsius, at 1 megapascal and then 35 degrees Celsius, right? So you check the points where it might be saturated, superheated, compressed, all those things based on the temperature and pressure, which we've spoken about before. Then you do the same thing for water. So water at 300 kP and 15 degrees Celsius, water at 300 kP at 25 degrees Celsius. So when we put all those terms in there, the only unknown becomes our MW. So we can make that the subject, and then we can find the mass flow rate of the water, right? So I'll leave this as something for you to try out so that to help you practice how to read from the tables. Now, we also have boilers. So boilers are a specialized kind of heat exchanger. So in this case, we have compressed water and we are converting it into superheated steam, right? So we have water and it's a heat exchanger because you are going to have heat coming from another source or another stream, and it's going to heat that compressed water, not just make it steam, it's going to make it superheated steam. So it's going to heat it even beyond the saturation point, right? So the heat source of which a boiler is applied can be hot flue gas from a gas turbine, fossil fuel, or biomass. So these are some of the sources or some of the fuels that we can use for a boiler. And for most conventional steam boilers, we can classify them as either fire tube or water tube. So these are just types of boilers we have, of steam boilers we have. And the kind of boiler, it depends on the place where the water is flowing. So what we mean by that is, for the fire tube boiler, water is going to surround the steel tubes, and then you have your hot gas flowing through the tube. So that's the fire tube boiler. So the hot gas is passing through the tube, but water is surrounding the tube. But for the water tube boiler, water will rather be passing through the tube, and then you have your hot fluid around the tube instead. So it just depends on the kind of configuration we are using. And then we can have um other kinds of um systems. So we can have economizers, vaporizers, superheaters. So things that can turn it just into a vapor, things that can superheat it beyond the vapor, things that would condense it, take it from the maybe take air from the atmosphere, use it for cooling, all these things. Right. So we have different kinds of boilers we can work with. So this is what we call a heat recovery steam generator system. So what's happening here is that we have a hot gas coming from a turbine and we have some water coming in here. So as the water is coming in here, realize that the hot gas is coming here. So the part that is red is hotter than the part that is blue. So there's a temperature gradient. This side is hotter, this side is cooler. So what happens is that as the water is flowing through, it's passing through a part of the gas that is hot enough to vaporize it. So the water gets here and some of the water gets vaporized. Right? Some of the water here gets vaporized. And then that vapor is still sent back into the system to be heated further to get superheated vapor. And that superheated vapor is now used to turn a steam turbine to generate electricity, right? So this is an example of what we call a waste heat boiler. Waste heat because the heat's coming from the gas that is leaving the gas turbine. We don't want it to just go to waste. So we are using that heat and we are trying to make our system more efficient. Are we okay with this? Please, are we following? Okay. So that's it for um this particular lecture. We'll be starting with the next topic very soon. But then something to take note of, uh we can't use the first law, or it's not prudent to use the first law for all process equipment. And we'll see why when we start with the next lecture, okay? And some of the principles that we can get from here, we can apply them to new equipment. So whenever you meet a new situation, it's reasonable to work with the principles we've used. Start with the first law, and then we incorporate the second law and the other laws as well. Right. So that's what we are seeing from this. So before I start the next topic, so this is the end of what we started yesterday. Before I start the next topic, are there any questions around this part so that we address them before we move on? Any questions? So are we all fine? Okay, then I think we can continue. So let me start the next one. A minute. Oh, okay. So we're about to start a very, very interesting topic, and this is on entropy. So please let's really pay attention. Okay, it's very important that we really pay attention to what we are about to do. Okay. So when we are done with this, we want to be able to explain the concept of entropy, how entropy is generated, the second law of thermodynamics, entropy balance for closed and open systems, and then the concept of isentropy, and then developing isentropic work for compressors and turbines. Okay, so when we talk about entropy, it's a property of a system as well, like enthalpy, internal energy, but it's a little bit abstract. So it's not really easy to give a physical description of how it's going to be without looking at things from the microscopic level, right? And to be able to do this, we want to compare or make a comparison with what we did when we were looking at work in a system, work being done in a system. So I'll explain that very soon. So I come to make some comparisons between work and then heat, right? To a fixed mass of gas in a piston cylinder arrangement. So remember when we were talking about our first law and we were looking at work being done, we said that uh, change in work, we can relate it to minus PdV, right? The boundary work. And if you look at this, this is a product of pressure and then change in volume. Pressure is an intensive variable, volume is an extensive variable. So the change in work is equal to minus PdV. So that's um, an intensive variable pressure multiplying an extensive variable volume. And we are keeping the pressure constant. Realize that for work to actually be done, or for we to say we've done work, then it means that volume actually has to change. So we want to do the same thing with heat now. So we know for heat, or before we even get there, let me move to okay. So what we are saying is that work that is applied or taken to a fixed mass of gas at a constant pressure will increase or decrease the volume. So that's what we are trying to say from here. That for work to actually change, when we are keeping pressure constant, it means that volume should have changed, right? And we are seeing here that there is no work done unless there is a volume change. So if we want to develop something similar for heat, we'll need two variables to develop the relation. Once again, we'll need an intensive variable and an extensive variable because we want to um, describe this the way we did for work. So for heat, the um, intensive variable we are going to have is going to be temperature. Is that okay? So temperature is going to be an intensive variable. And then there's going to be another variable that is going to be extensive. But just like what we did for work, where volume had to change for we to say work should be done, that variable that we are going to define should also change for we to say that heat has been transferred, right? And that variable is what we are going to represent with entropy. So what we can say at the end of the day is that, I think, let me write it here. What we can say at the end of the day is that just as we had dW is equal to minus PdV, we can say that the Q, right, that's a change in heat, should be equal to T. So that's going to be our intensive variable, right, times a change in something. That something is what we are representing with entropy. It has the symbol of S. So what we can say is that for we to say that heat has been transferred, then it means that there has to be a change in entropy. So now it is looking similar to what we did for the change in work being equal to minus PdV. Okay. Now, as we said, we are going to call this property entropy, and it's an extensive variable. We can divide by the total mass to make it intensive, right? So we said that here, dQ is equal to TdS. The subscript ReV here means reversible. And when we see this means internally reversible. So we'll see what they all mean very soon, right? So we already said that dQ is equal to TdS. If I make the S the subject, I'll have dQ over T. So that's what we can see over here. And we are doing this for what we call internally reversible systems, right? So when we say a system is internally reversible, or when we say something is reversible, it means that we have the ability to start at a point, go to another point, and then come back to the initial point, right? So it's reversible because I can start at A and go to B. But when I get to B, I can easily come back to A as well. So then I'm reversible. But then when we say something is internally reversible, what we are saying is that it is reversible, but then the only thing that we are considering reversible is the system itself. So what we mean by that is, for reversible situations, something can be reversible where we are considering both the system and the surrounding together. Or when we say it is internally reversible, then we are considering just the system. Is that okay? Okay. So we have this expression on the left here. If we should integrate both sides, the ds will become delta s. And then we'll have integral of our del q over t, right? The units for entropy based on the dimensions are going to be kilojoule per kilogram. Because you know that our change in heat will be in kilojoule, our temperature will be in, sorry, kilojoule per Kelvin. Our change in heat is going to be in kilojoule, our temperature is going to be in Kelvin. We work with absolute temperature. Please take note of that. The temperature is in Kelvin. So the unit is going to be kilojoule per Kelvin. And if it is specific, we are dividing by mass. So we'll have kilojoule per kilogram Kelvin, right? So from the equation above, entropy change is equal to the reversible transfer of heat between a process and its environment. Is that okay? Okay. So when we talk about entropy, what we are saying is that entropy is a measure of randomness or disorder of a system. So we can have molecules being arranged in a vessel. But when we talk about entropy, what we are saying is that those molecules are not going to be kept in their ordered position. As time goes on, as heat is coming in and work is being done and all these things, they are going to become more randomly dispersed and moved about. So there's some kind of disorder, chaos, and randomness in our system, right? And entropy, as we already said, is a state function, just like enthalpy and internal energy. So its value would increase with an increase in the number of available microstates or macrostates. So what we are trying to say by this is based on some statistics and some probability that they use to determine these things. But what they are trying to say here is that, or a microstate, what we are saying by that is it's an arrangement of all the possible positions and energies that your particle can have. So maybe I have a situation where my particle can occupy position A, B, C, and D, or it might have this amount of energy at different locations, right? if I increase that, if I increase the number of possibilities, if I increase the number of possible locations my molecule can occupy, then I'm in effect also increasing the entropy, because I can increase how um more disordered it can become. So this is what I'm just trying to say. Imagine I have a system this way, and then the only available sites are 1, 2, and 3. These are the only available places that my molecule can occupy, right? And then I have another case where I have 1, 2, 3, and then 4. If we are supposed to randomly place a molecule, right, cause some form of disorder, for the first case, it can only occupy 3 possible places. So the second case, it can occupy more places. So there can be more disorder here. I can make it more random in the next case. So we are just saying that if there's an increase in the number of available microstates, then there's an increase in the entropy as well. And then the macrostate is just a collection of microstates, right? So these concepts of entropy were developed by people such as William Rankine, Rudolf Clausius, and then Ludwig Boltzmann. So you come across their surnames in a lot of applications very soon, right? And one of the most important laws that really explains the concept of entropy is what we call the Clausius inequality. So that's what we are coming to look at now. So Clausius came up with an inequality, and what he said was that for every thermodynamic system, right, we have this expression. Now, if you see an integral sign with a circle on it, it means it's a cyclic integral. It means that you're doing your integration over something that is a cycle. So let's look at this image we have on the right here. We have a situation where I can move from point 1 to point 2, and then from point 2 back to point 1. So that's a cycle, right? So if I should integrate over a cycle, it means I'll first integrate from point 1 to point 2, then I'll integrate from point 2 back to point 1. So that's a cyclic integral. And we've already spoken about this del Q over T term, which is going to be related to our entropy. The subscript here, the B here, is representing the boundary. So we are looking at the change in heat per temperature at the boundary of our system. That's where we are doing our integration over. And Clausius said that this should be less than or equal to 0. So when we look at thermodynamic cycles, you would get the understanding a bit more. But then just to, should I do, okay. Let me project this one. Sorry, a minute. I think so. The way we went about it is that we have a certain source that is going to generate some amount of heat, right? Or it's a reservoir, it has a lot of heat there. And then whatever heat is coming out of, it's coming out at a particular temperature. There's going to be a change in heat as it's moving. Now we want to send this to what we call a reversible heat engine. So a heat engine is just something that is going to take heat from a source and then convert it into work. So it's going to convert it into some form of reversible work, right? But then the thing is that if we keep it like this, what we are saying is that all the heat that is coming in is being converted to work, and that is not possible in reality. So it means that not all the heat that is coming in can be converted. Some of the heat has to come out, right? So we represent that with del QE. There's some amounts of heat that will also come out. So you're just looking at the small amounts of heat that are being transferred, and it also come out with its at its own temperature, right? But then this heat that is coming out, it is not going to nothing. It's going to something, even if it is a surrounding. So we'll have another system that is going to be receiving that heat. But when the system receives heat, this heat can also be transformed into work again, and then there will still be some amount of heat left, right? So once again, all the heat is not going to be transformed into work. So this is just one thing to take note of. And then the broken line channel are just showing where we are doing our balance. So we are just doing a balance for them where the broken line is. And we are considering that we are working with a closed system. So since we are working with a closed system, we are considering that heat is moving, not mass. right? And we are looking at the small changes that are going to occur. So the small change in the heat that are going to occur, the small changes in the work, and then we can integrate over the entire system. Okay, someone says they are lost. Which parts would you want me to take it from? Were you able to follow up to this point? Were you able to follow up to this point? Okay. So what we're saying was that there's a certain inequality that we use called the closures inequality, and it helps us really understand entropy better. But we are saying that it's supposed to be less than or equal to zero. And we've already talking about the del Q over T expression, right? So what we are saying is that I'll start that one again. So what we are saying is that if we want to consider a system, we have a system where we have a lot of heat, right? That can be generated, that is being stored. Now we want to use this heat to do some amount of work. So what we do is that we send it to what we call a heat engine. A heat engine is just a device that will convert heat into some form of useful work, right? So at this heat source, there's some amount of heat. It's coming out with a particular temperature. And we're just looking at the small changes in heat, right? So it's coming out at a particular temperature, and then there's some amount of heat coming out, and it goes to the heat engine. So the heat engine is going to develop some amount of work. That's what we have here. But what we're also saying was that we won't have a case where all the heat coming in is going to be converted into work, right? So some of the heat is definitely going to come out. And when some of that heat comes out, it will come out with its own temperature. So we have some amount of heat, a very small amount of heat. We are looking at small amounts of heat being transferred and then some temperature. And what I'm also saying is that this heat that is coming out, we are not just going to leave it to go to nothing. It will definitely go to something. Even if it is a surroundings, it's going to something. So that heat is going to end up somewhere else. So usually we can call this a heat sink where heat is going to, yes, be stored, right? Now, when it gets here, that heat that gets in here can do some amount of work, right? It can cause the system to do some amount of work. So some amount of work can be generated by the system. And then there will still be some amount of heat left in the system. Are we okay with that? Are we okay with that? Okay. So what we are seeing now is that we are working with a closed system. Okay. So what we are saying is that we are working with a closed system. So we are looking at the movement of heat, not mass. Right. So we are looking at heat moving through our system. We are looking at just the small changes in heat. When we get all those small changes, we can now integrate to get the overall expression we need. Okay. So we'll start with our first law expression for reversible systems, right? So, and for closed systems. So we know that the change in energy is equal to the change in Q plus the change in W. We're looking at the small changes. And we know that in this case, the W, the total work that we are going to get is going to be the work being done by the engine and then the work being done by the system, right? Now, the work that is being done by something, remember we said it was going to be negative. So it will be negative del W or a negative del W of the system. Not for the change in the work. So we can put that into the first expression so that we have a change in energy to be equal to this. Now, if we compare the ratio of heat at 2 points, it's equal to the ratio of temperatures at those 2 points. So what I mean by that is, if I look at the heat here and divide it by the heat here, is equal to the temperature here divided by the temperature here, right? So what we are doing right now, you would apply it even to the very next lecture, the one that is after entropy, where you deal with thermodynamic cycles. So please really take note of these things. So the amount of heat here divided by the amount of heat here is equal to the temperature here divided by the temperature here. Okay, sorry, I'll slow down a bit. In the same way, the amount of heat here divided by the amount of heat here is equal to the temperature here divided by the temperature here. So all that we are trying to say is that if I should find the ratio of heat between 2 points, it's equal to the ratio of the temperatures between those 2 points. Is that okay? So that's the expression we have. So I can look at the heat from the heat source and then the heat from the engine and then compare them. So I can say that my del QH over my del QE should be equal to TH over T. So that's what we have here in expression 1. And I'll make del QH the subject to get this. In the same way, I can say that if I'm comparing the engine and then the system, I can say that del QC over del QE is equal to TC over T. So if I do that, I have this expression here. I can make del QC the subject and I'll get what I have for equation 2. Now for the del Q, the change in the heat is going to be what is coming out, right? For where we are doing the balance, minus what is coming in. So what is coming out is going to be our del QC. What is coming in is our del QH. So that's what we see here, that our del Q is the out minus in. That's del QC minus del QH. Or we've already expressed del QC and del QH in equation 2 and 1. So I can just put those expressions in there directly, right? And then I can factorize del QE over T out. And I'll have this expression down here. Del QE over T times TC minus TH. Are we fine up to this point before I continue? Please, are we fine? Okay. Amanda, which part would you want me to go over? Which part, please? Okay, a minute. From the first equation explanation I gave. Am I talking about the del QE part? Okay. So this is what we are saying. Del QE, remember when we're looking at the first of thermodynamics, we said that our change in energy of the system is equal to Q plus W. And remember we cancelled out kinetic and potential energy and we had change in U is equal to Q plus W, right? So what we are doing is that we are looking at very, very small changes now. So the small change in the energy of the system will be equal to the small change in heat plus the small change in work. That's why we are using the del symbol. We are just looking at small changes. And if you look at the change in work, right, or the amount of work that is being done, we have del WR, the work that is coming from the engine, and then the work that is coming from the system. Remember, we said that work that is done by something is negative. So our del W will be negative del WR and then negative del W of the system. Are you fine up to that point? So I just put the del W, that expression we found, into the first equation. Is that okay? Okay. Then what I was saying was that there's something that we need to know. So there's a relation that we need to, okay, that's good. The relation we need to take note of. So if we compare the heat between 2 points, right? The amount of heat at 2 points, it is equal to we comparing the temperatures at those 2 points. So if I'm looking at this point, let me, if I'm looking at this point and I'm looking at this point, I can take the heat here. So that's the del QH and divided by the heat here, that's the del QE. It should be equal to the temperature here, that's TH, over the temperature here, that is T, right? Or I can decide that I'm going to compare maybe the heat coming from the engine and then what is coming out of the system. So maybe I'm going to compare the heat here to the heat here. So I can say that del QC over del QE will be equal to my TC over my T. So if I just compare the heat at 2 points, it should be equal to the comparison of the temperatures between those 2 points as well. So that's what we have for equation 1 and 2. And we just made del QH and del QC the subjects, right? So del QH over del QE is TH over T. Del QC over del QE is TC over T. Then we made del QH and del QC the subject. The reason why we are making those the subjects are because the heat that is coming in to the system where we are doing our balance is del QH. And what is coming out is del QC. So we are looking at the inlet and the outlet, not what is in the middle. Right? That's where we are going to find our change in Q. Is that fine? So our change in Q is going to be based on what was coming out and what was coming in. Is that okay? Okay, that's good. So now we know our del Q is the out minus in. That's the del QC minus the del QH. And we know that del QC, according to equation 1, is going to be this. And then for del QH, according to equation 2, is going to be this. So I can subtract them. But then they both have del QE over T in their expression. So I can factorize that out. And I'll be left with TC minus TH. So del Q becomes this expression at the end of the day. Now, remember we said from this point here, del QE was del Q minus the work expressions. So I can replace that del Q with what I have here. So I can put that into this expression and I end up with this last expression down here. Right. So right now we're just substituting. We're just putting it back into the expression. Yes, please. We are finding the heat change of the system, not the one in the middle, yes. By the end of the day, it would have a relation to what is in the middle. But yes, you are doing out minus in what was coming out minus what was coming in. Okay. So we ended up with this expression after we did our substitution. Now we see negative WR and then negative WS. So we can factor the negative out and then have it to be positive. Right. So when we do that, we end up with this expression now. Now, please take note of this. Remember, we spoke about the fact that we are dealing with a cycle. So if we are integrating over an entire cycle, right, the change in E goes to zero because we set up for a cycle, there is no change in internal energy, especially when we assume kinetic and potential energy go to zero. For a cycle, there's no change in the internal energy or there's no change in the energy at the end of the day, right? But then the heat and then the work terms can change. So the del E goes to zero. So if this goes to, if I'm integrating everything, this goes to zero. I'll integrate the first term. So that's what I've done down here. And I'll integrate the second expressions. That's what I have down here. Is that okay? And remember, I said that if you have an integral with a circle, it means it's a cyclic integral. So we are doing the integration over a cycle. Now I can send this part here over the equal to sign. So if I do that, I'll have this expression now. Is that okay? And one thing to note, TC is colder than TH. So it means that TC minus TH is going to be negative. But now the work expressions we have here are now positive. When we send them over the equal to sign, they are now positive. So if we are having the summation here to be positive, and we're having a negative term in here, it means that whatever that negative term is multiplying should also be negative for it to become positive. So here I have positive, and it's equal to something multiplying a negative, right? For it to be equal to each other, it means that this x here has to be negative as well. Or this x can be zero. If the x is zero, then it means that the expression I have here is zero, right? It means that there was no work, there was no network that was being done. Is that okay? So if we, let me clean that part. Okay, so if we set TC minus TH, which is going to be a constant, is less than zero or equal to zero, right? Because TC has to be less than or equal to TH. If TC is more than TH, then heat is being transferred in the other direction. So TC is colder than TH. That's why heat is transferred from the hotter part to the colder part. So Tc is lower than Th. So that part is less than or equal to zero. But we know that our del Wr and our del Ws are greater than or equal to zero. So for it to make sense, for it to be balanced, then it means that whatever is multiplying the Tc minus Th has to also be less than or equal to zero. And that's where that equation was coming from, right? So if we come back to the entropy slide, that's the expression we have here, where our del Q over T, the cyclic integral of that is less than or equal to zero. Is are we fine with this so far? Okay. Now, we are saying that if no irreversibilities occur within the system, right, then the system can be described as internally reversible. So remember I said that when we say something is internally reversible, it means that when we consider just the system, right, it is reversible. So there are no irreversibilities that are happening in the system. But then if we compare maybe the system and the surrounding together, it could be irreversible. But then within the system alone, it is reversible, right? So when we have a case like that, we say it is internally reversible. And when it is internally reversible, then the closures expression is equal to zero. So please take note of that. When it's internally reversible, it's equal to zero. When it is not, then it is less than zero. Remember, we said that the expression is less than or equal to zero. So if it is less than zero, it is irreversible. But if it is equal to zero, then it is internally reversible. So please take note of these things. Sorry, someone called. So we are saying that if we have a cycle that consists of two processes, so we have process one to two, we are moving from one to two, right? And then we will move from hello. Okay. So what we are saying is that if I have a process, I'm moving from one to two, and I can move from two back to one, right? So now it's a cyclic process. But when I'm moving from one to two, it is reversible or it can be irreversible. But then for the part that I'm moving from two back to one, for that one, it is internally reversible. So that's what we are considering for this cycle. So one to two, it can either be reversible or irreversible, considering both the system and then the surrounding. But then from two to one, we are considering just the system. We are saying that it is internally reversible within the system. Now, remember we said we are doing a cyclic integration. And I said when we are doing a cyclic integration, we'll do the integration over one path and then integration over the other path as well. So I can do the integration from path one to two and then from path two to one. Is that okay? Is that okay? So if we look at the expression down here, for the cyclic integral, we're doing the integration from one to two. That's the first expression they have here. That's this first expression over here, from one to two. And then from two to one, we said it is internally reversible. But remember, once again, we said that that whole expression should be less than or equal to zero. Now, remember we said that when it is internally reversible, then we are just considering the system, right? So we can look at the state of the system. And that's where this comes in. So all that this is trying to say is that if I'm moving from two to one, because I'm just considering the system, I can look at the entropy when the system was at point two, and then the entropy when the system was at point one, right? And then the change in the entropy. So from two to one will be final minus initial. I was moving from two and I was ending at one. So the final is going to be S1, the entropy at point one, minus S2, where it was coming from. Is that okay? So that's where that expression is coming from. And that one only holds for the part that is internally reversible. The one that is just dependent on the system or the state that the system is at. Please, are we okay with that? So I'll take that part again. So what we are saying is we can start with this inequality we have here, the closures inequality. But we are saying that if it is a cyclic integral, then we are doing it over a cycle. So I'll first do my integration from point 1 to point 2. And that's this first thing we have here, from point 1 to point 2. Then I'll do the integration from point 2 to point 1. So that's what we have here. But we said that that part, we are assuming, or we are taking it to be internally reversible. And we said internally reversible, it is reversible, but then within the system. So we are just considering the state of the system. We are not considering the system and its surroundings. We are just focusing on the state of the system. Since we are considering just the state of the system, at point 2, I can find the entropy of the system at that point. At point 1, I can find the entropy of the system at that point. And if I should do the integration from point 2 to point 1, right, I'm just going to end up with S1 minus S2 at the end of the day. Please, is that okay? So it means that this whole expression here now, the part that is internally reversible, I'll replace it with S1 minus S2. And that whole expression should still be less than or equal to 0, starting from what we spoke about over here. Is that fine? Okay. Now, if we decide to send this part over the inequality sign, oh no, sorry, it was rather the S1 minus S2 they sent over. We'll get S2 minus S1 to be greater than or equal to the integral that is left. So that's this expression here. Now let's look at this. If we are saying that S2 minus S1 is greater than this expression, right? What can we do to make sure that the expression is equal to S2 minus S1? It means we'll have to add something. If I say that 3 is greater than 2, for me to ensure that 2 is equal to the 3 now, it means I have to add something to the part that is less than. In this case, it will be 1. Is that okay? And please mind you, the question said is less and greater than or equal to, right? So 3 can be greater than or equal to that expression. So if I'm adding a term, then that's what we have here, S generated. So that's the amount of entropy that is going to be generated. Is that okay? Now, what we are saying is that S generated, if it is greater than 0, then it means we have an irreversible process. Why is that so? Because if it is greater than 0, then it means that indeed this expression here was less than the expression on the left. And if that's the case, it is less than what we were going to assume for an eternally reversible system. So it means it is irreversible. But if it is equal to 0, then it means that this expression here was already equal to S2 minus S1. So if this was 0, it means that it was already equal to S2 minus S1. So it was already a reversible process. Is that okay? So remember we said when we are moving from point 1 to point 2, we are assuming that it can be either reversible or irreversible. The way we can determine that is by the value we get for S generated. If S generated, that's the entropy generated in the universe. If S generated is greater than 0, then we have an irreversible process. If S generated is equal to 0, then we have a reversible process. Right, so let me use the example we used again. Remember we said if 3 is greater than or equal to 2, right? Because this is less than, so let's say 3 is a reversible process. 3 is the standard for a reversible process. And for a reversible process, that's the highest possible thing you can get. So let's say 3 is a standard for a reversible process. Because 2 is less than 3, it means 2 is irreversible. So I had to add something. And that thing I have to add has to be positive. It has to be greater than 0. So because I'm adding something positive to it to make it reach that thing, to make it reach what it would have been for it to be reversible, it means that it was less than what I was dealing with at first. Is that okay? So for this value here to be positive, it means that what I have here was already less than what I was working with. So because it is positive, it means that this was irreversible because it was less than the value that we're expecting for it to be reversible. So when it is greater than 0, when edge generated, that added term is greater than 0, then we say it's an irreversible process. But then if we had a case where we had 3 is greater than or equal to 3, right? I don't need to add anything to it. If I'm adding something, it's going to be plus 0. So it means that what's if I have this, it means that basically 3 is just going to be equal to 3 at the end of the day. So because I don't have to add anything to it to make it reach the value that would have made it reversible, it means that the system itself was reversible. So when our edge generated term is equal to 0, then it is reversible. Now, if our S generated term is negative, right? It's going to be an impossible situation. So it cannot hold, it cannot work. So once again, imagine I have 3 greater than or equal to 4. In order for me to make it equal, this has to be negative. I have to bring a negative in there. The moment a negative comes in there, it means that what I was dealing with was greater than what I was expecting for it to be reversible, which was 3. And we can't have something greater than the reversible point or the situation where we are assuming it is reversible, right? So it means it's going to be impossible. Is that okay? Please, I hope you get what we are trying to say. So the summary of this part is that we have this expression over here. If we want to make them equal, it means we have to add a certain term to the right-hand side so that it becomes equal to the left-hand side. But if what we are adding to the right-hand side is equal to 0, then it means that what is at the left was already equal to what is at the right. And what is at the left is representing a reversible process. Is the highest thing we can get. We can't just go higher than a reversible process, right? So that's where we can get our maximum work, the maximum use of heat, all those things for reversible processes. So we can't go higher than that. Now, if it is equal to 0, it means that it is exactly equal to a reversible process. If it was greater than 0, then it means that what was here was originally less than a reversible process. So if it is less than that, then it is irreversible. But if it is negative, if the Sgen here is negative, it means that this value here was originally more than the reversible process, which is not possible, right? So this is just something for you to take note of. So at every point in time, the entropy that we are going to generate is going to be greater than or equal to 0. And mind you, this entropy that we are generating, we are looking at it from point 1 to point 2. We didn't put the internally reversible subscripts there. So this entropy that is generated is not just for the system alone, it's for the system and its surroundings. So we are looking at the entire universe, right? A system within the universe. So the amount of entropy that is going to be generated in the universe is always going to be positive or equal to 0. So that's the second law of thermodynamics. So remember when we were ending the previous lecture, we said that it's not the best to only use the first law for all cases, but we can always start from there. But sometimes if you just work with the first law, you might be working with a system where the entropy generated is less than 0. The entropy generated in the universe is less than 0, which is not possible, right? So we'll look at the effects of entropy. So processes can occur in a certain direction only. So we'll see examples of what we mean by that, right? They proceed in a direction that complies with the increase of entropy generation. So that means that when we are looking at processes, the only processes that can actually work are the processes where our entropy generated is greater than or equal to 0. So it has to follow this principle. And we are also seeing that entropy is a non-conserved property. So entropy is not like mass and energy that is fixed in the universe. No, entropy can be changing. The only situation where entropy is conserved is when we have something that is internally reversible, adiabatic, there's no heat transfer, all those things, right? That's the only case where we can see that entropy is conserved. And even that one, it is only conserved within the system. It's not conserved in the entire universe, or it's not conserved between the system and its surroundings. So the performance of engineering systems is degraded when we have irreversibilities. And entropy generation is a measure of the magnitude of the irreversibility we have, right? So we are seeing here entropy generated is a measure of the magnitude of irreversibilities that we have. So please just take note of that. All we are just trying to say by that is if I have a system, right, and there's no point that is reversible, right, then I'm dealing with irreversibilities. And entropy is just measuring how irreversible it is. Is that okay? Okay. So these are examples of the effect of entropy. So remember we said over here that it can occur in a certain direction only. You're coming to see examples of that. So if I have a cup of hot coffee and I leave it in a cold room, the cup will eventually cool off, right? It will lose heat to the room. But then if I have a cup of hot coffee left in a cold room, the cup of hot coffee cannot become hotter, right? We can't leave it just there and then have heat moving from the cold room to the cup unless we like intentionally force something. Is that okay? So in that case, we realize that it's just one direction that our system can move in. If we're basing it on just the first law principles, we may end up with a situation where we can assume that heat can also move from the cold room to the hot coffee on its own, right? Another example, we have air held at a high pressure in a closed tank and it flows spontaneously to the lower pressure if the valve is removed. So we can have air moving from higher pressure to lower pressure because that process, that path, right, allows for the second law to hold. It allows for Sgen to be greater than or equal to 0. But in the case where we are moving from lower pressure to higher pressure, cannot happen because if we should try that, we'll be getting Sgen to be less than or equal to 0, right? So entropy generation will place a limitation on the amount of work that a turbine can also generate. So we are saying that if we look at a turbine working, right, it's maybe ideally should be able to generate this amount of work. But because there's entropy being generated, it wouldn't generate that amount of work. So let's say that all your inputs that you are placing into the system, some of it goes into work and some of it is lost. What is lost ends up contributing to entropy, right? So we can see this in things like frictional losses and all of those things. So when we talk about the effects of entropy generation, what we are saying is that the quantity of energy is always preserved during an actual process. So that's from the first law, right? But then the quality is bound to decrease. So that's why we can have a system that is 100% efficient. Some of it is going to be converted into something else and will contribute to entropy. So that's this decrease in the quality is always accompanied by an increase in entropy. So heat, in essence, is a form of disorganized energy, and some disorganization would flow with heat, right? So that's where entropy comes in. So as heat is moving, there's some amount of it that ends up contributing to disorganization of molecules, causing them to become more randomized. So that's contributing to entropy. Okay. Now, we've already spoken about this. What is a reversible process? So we said a reversible process is just a process that we can reverse without leaving any trace on its surroundings. So I can start from A and go to B, and I can just move from B back to A, and it will look as though nothing ever happened, right? So if we have a process that is reversible, please note we are considering that both the system and the surroundings are returned to their initial state at the end of the process, right? So if it is reversible, we are looking at both the system and the surrounding. If it is internally reversible, we are looking at just the system. Please keep note of these things. Okay. Now, sources of irreversibility, we can have friction. So we can have unrestrained expansion, something that we are not controlling, and then it just begins to expand. We can have heat transfer due to a finite temperature difference. So these are things that would introduce some kind of irreversibility. We can't reverse them, right? So imagine we are working with a system and then there's some amount of friction. We can't say that we are going to take the friction and process that just happened and then reverse it to get back our work. It's not going to be possible, right? So engineers are interested in reversible processes because, and this is the main thing, is because work producing devices such as car engines and gas steam turbines deliver the most work, right? So if you have a system that is reversible, remember we said this earlier, that a reversible process is the highest thing you can achieve. You can't go beyond that. If you have a reversible process, it is going to deliver the most work possible, right? And if it is going to consume work, then it's going to consume the least work possible. Is that okay? So you want a system that can take a little amount of work and do a lot of work. That's where reversible processes come in. So it's only reversible processes that can use a smaller amount of work and deliver a lot more work when you compare it to irreversible processes. Okay. So we've said this, that a process is totally reversible or simply reversible if there are no irreversibilities within the system or its surroundings, right? So a system that is totally reversible, there is no heat transfer through a finite temperature difference. Finite temperature difference is just saying that I have the temperature at one point to be A and at one point to be B. I'm just finding the temperature difference between them. I'm not looking at the small changes in temperature. There is no non-quasi equilibrium change. So we've spoken about quasi equilibrium changes already. That's very, very slow changes, right? And then there are no friction or dissipative effects. Dissipative is just like something being lost. So if you are saying heat is being dissipated, we have heat in the system and it's just being lost to the surrounding, right? So there are no friction or dissipative effects. So if only the system is restored, then the process is internally reversible. So if we can bring the system back to what it was originally, just the system, then we say it is internally reversible, right? So before I continue, I'll just ask, are there any questions up to this point? Does anyone have any questions? Does anyone have any questions? Okay. With the points you feel I'm going fast, please prompt me, okay? And I'll slow down and I'll go over it again. But is there any specific points you want me to go over? Is there anything you'd want me to go over? Is there anything? Okay, sure. Then let's go on. So we said entropy is a property, it's a state function. So we can use it to determine the state of our substance, right? We are looking at entropy for a pure substance now. So remember when we did our phase diagrams, we're looking at temperature against specific volume, pressure against specific volume, pressure against temperature. We can have a similar graph when we consider temperature and then entropy, right? So we can have a very similar graph. And then we can read entropy values from property tables the same way we read internal energy, specific volume, and then enthalpy. So we can go to a table, maybe our ideal gas table, our refrigerant table, our steam table, and then we can read entropy at a particular temperature, at a particular pressure, under certain conditions, right? And then just as we saw when we're looking at the expression for the quality of a vapor liquid mixture. We can also have the entropy of a mixture to be equal to the entropy of the liquid plus the quality being multiplied by the difference between the entropy of the vapor and the entropy of the liquid. So we've already seen this expression before. Is that okay? Now, what we are seeing is that because of the effect of entropy on the efficiency of systems, remember we talk about the fact that entropy helps us to determine how efficient our systems are. So if we have a system that is reversible, we have a high efficiency. If it's irreversible, or if there are lots of irreversibilities, we have a lower efficiency. Because entropy can be used to determine the efficiency of the system. When we are working with thermodynamic cycles, you're not so interested in pressure volume diagrams or temperature volume diagrams, but that prefer temperature and entropy diagrams. Is that okay? Because we work a lot with temperature, we want to see the effects on entropy as well. Okay. So we'll be ending um with entropy balance and we'll take an example, right? When we say um entropy balance, we can look at it just like all the other balances we've done so far. So we know that the total entropy, the graph, okay, let me go through the graph. So just as we did for um pressure volume, temperature volume, right? What we are saying is that if I should start out as a liquid, so let's say we are working with just this line for now. Because remember that this graph is coming from a collection of um different lines at different conditions. So we are working with this line for now. This one is at 1 megapascal. What we are saying is that when I'm starting out here, I'm a liquid, right? So at that particular temperature, I'm a liquid, and my entropy is a bit low. But then as I continue to increase the temperature, I get to a point where I now fall on this point. When I get to this point, I'm no longer just a liquid. I'm a liquid that can now begin to change to a vapor. And remember we said for phase change, temperature is constant. That's why the line becomes straight. The temperature isn't changing. So this is the temperature axis. The temperature isn't changing. Then, I mean, the liquid will be changing to vapor, be changing to vapor until it gets to this point where it is fully vapor. At this point, I can increase the temperature further. When I increase the temperature further, the entropy will increase more. The reason why we are seeing the entropy increase is because as we are increasing temperature, What we are doing is that we are causing the molecules to become more disorganized. That's why it can even start to move apart and then now start turning into a vapor. So all we are just trying to say is that as we increase temperature, the entropy of the system would also be increasing. Is that okay? So that's what we are just seeing from the diagram or from the graph. Okay. So when we look at the balance, right? Remember for all our balances, we always say that it is what is coming in minus what is coming out plus what is being generated being equal to the total change at the end of the day. Being equal to the total change at the end of the day. Right. Okay. Now, we are seeing here that the entropy balance usually solves together with the energy balance. Okay. Now, when we look at the change in the entropy, right? So that's this part here. Let me use this is the change in the total entropy of the system. That's what you're representing with this here, right? Then the entropy entering and the entropy leaving is what we're representing with this over here. Then the entropy generated is what we're representing with this. So this is the entropy that is being generated. Is that okay? We see why this part here is going to give us the entropy entering and then the entropy leaving. So remember we said if I have a process, I'm moving from maybe point 1 to point 2, right? The entropy entering the process is coming from point 1, and I'm moving to point 2. So the entropy leaving the process is coming from point 2. So if I should do the integration from point 1 to point 2, I'm in effect finding the total entropy entering minus what is leaving. Is that okay? So for a closed system, heat is the only means by which entropy can enter the system. Because for a closed system, we don't have mass being transferred across the boundaries of the system. It's just heat. So the only way that entropy can get into the system is when there is heat. So for the system, there is only a net heat gain or loss. So the entropy balance, we can write it for different cases. In a case where we have just one reservoir, a reservoir is just talking about a source of heat, right? So when we have just one source of heat, then we can write it in this form. It's just one place heat is coming from. So let's say this is our the boundary of our process. Let me do it this way. Let's say this is the boundary of our process, right? There's a certain amount of heat that is coming this way, and it's coming at a certain temperature. At all points, it's the same heat and it's the same temperature. So surrounding the entire thing, right? So I can represent this part here, the in minus out part, with just the Q over T. But in the case where I have, sorry, more than one location or more than one reservoir, more than one source of heat, I'll have to add all of them, their values. So I'll take the Q of the first part and then the temperature at that part. So let me put it this way. So let's say I have here Q and T. And then I have here maybe Q1 and then T1, right? All we are saying in effect is that for me to now find this part here, instead of me just doing Q over T, once I have multiple locations now, it will be Q over T plus Q1 over T1. That's what we are just trying to say by this over here. Right? So then we have different locations on the boundary where we can have heat being transferred. Then we can use that expression. Then when we are dealing with an isolated system, the change in entropy for an isolated system, right, is going to be equal to the entropy generated for an isolated system. Because remember, for the isolated system, if it's isolated, we don't have energy or material coming in or out. And we said that the entropy that would have come in if it was closed would come in because of heat energy. So if there's no energy coming in or out, then it means that the in and out terms for entropy will also be zero. So the entropy change for an isolated system is just going to be the entropy generated. And the entropy generated, we'll consider the entropy that is generated in the system and what is generated just around the system. Is that okay? So for an isolated system, this is going to be the final expression that we are going to get for the entropy generated, right? So all we are just trying to say in effect is that when we are dealing with an isolated system, because there is no heat or mass being transferred across the boundary, all we are going to see is that there's not going to be any entropy coming in or entropy leaving. So they go to zero. So all I'll be left with is the entropy generated to be equal to the change in entropy. That's what we are trying to see. And that change in entropy is going to be the entropy that would change within the system and what's going to change just around the system. Okay, so we'll be ending with this example. Okay, I think okay, we can finish it on time. So we have an example here, right? It says consider steady heat transfer through a 5 meter by 7 meter brick wall. So the question said it's a steady heat transfer through a 5 meter by 7 meter brick wall of a house of thickness 30 centimeters. They're giving us the length, breadth, and then the thickness of the wall, right? On a day when the temperature of the outdoors is 0 degrees Celsius, the house is maintained at 27 degrees Celsius. I think let me open this slide instead and use that one to go through the question. Um, okay, this is it. Good. So this is the question, the same question. So we have steady state heat transfer, right? That's a very important point to note. We'll see why very soon. And we've been given the dimensions of the wall. Now we are being told that on a day when the temperature of the outdoors is 0 degrees Celsius, the house is maintained at 27 degrees Celsius. The temperature of the inner and outer surfaces of the brick wall are measured to be 20 and 5 degrees Celsius respectively. And the rate of heat transfer through the wall is 1035 watts. To determine the rate of entropy generation in the wall and the rate of total entropy generation associated with this heat transfer process. You're going to just consider the wall. So this is what the question was saying, if you should represent it with a diagram. The question is saying that on the wall surface, right, the outer surface is at 20 degrees Celsius. The inner surface is at 5 degrees Celsius. So that's what we see here. The inner and outer surfaces of the brick wall are measured to be 20 and 5 degrees Celsius respectively. And we're also told that at the outer part of the wall, the air there is 27 degrees Celsius. And on the inner part of the wall, that's inside the house, the temperature of the atmosphere or the environment there was 0, right? So we see here that on a day when the temperature of the outdoors is 0, the house, no, I think it's the other way around. The temperature of the outdoors rather supposed to be 27, and then the indoor was supposed to be 0. So sorry, there was a switch there. Right, so outdoors is 27 and then indoors was 0, right? So we see that there's a temperature gradient, 27 to 20 to 5 to 0. Now, we know that a change in entropy, the question said we should find a change in entropy or the entropy generation in the wall. So we are just considering the wall for now, right? So we'll still start with this general equation where a change in S is equal to this expression plus our S generated. Now, the question said that we are working at steady states. Remember that we said entropy is going to be dependent on the heat and then the temperature, right? Now, if we are at steady state, it means that at every point in time, there's not going to be a change in the heat at every location. And the temperature there is also going to be fixed. So the change in entropy at the end of the day would have to be equal to 0. So because it is at steady state, this change in S is equal to 0. Or if you want it in another way, remember we said for energy balance, in minus out plus generation should be equal to accumulation. And when we are dealing with steady state, we said accumulation is 0. So this here is representing an accumulation term. So we can go to 0 because we are at steady state now, right? So we are seeing that there's supposed to be no entropy change in the wall. So delta S can go to 0. Now, we are doing this from point 1 to point 2. And remember, I talk about the fact that if we are doing it that way, we can take it as entropy at point 1 minus entropy at point 2, right? Plus the entropy generated to be equal to 0. So remember, we said we can express this as S1 minus S2. Okay. So we have that expression S1 minus S2 plus S generated to be equal to 0. But remember, we also said that our S1 we can represent it with Q over T. So that's what we were seeing from this slide. That's what we were seeing from here, Q over T, and here Q over T, right? So that's what we are just seeing at this point. So we can represent it with Q over T. So I can have my Q1 over my T1 minus my Q2 over my T2, my Q2 over my T2. Sorry, right? And the question gave us the value for Q as 1035 watts. It was constant throughout, so it's 1035 watts too. And then the temperatures were the difference. So we take the temperature on the the outer part of the wall, and then the temperature on the inner part of the wall. So that's what we have. Now we need that temperature to be absolute. When we are doing these calculations, please always make sure temperature is absolute, right? So we change it to Kelvin. That's why we are adding the 273. So when we do this and we make SGen the subject, we'll get this value. But remember, this was for just the wall. That's why we use the 20 and then the 5. The question also said we should do the same thing for the entire process. So the rate of total entropy generation associated with this heat transfer process. So that's for the entire process. So we repeat the same procedure, right? We'll simplify it to the same expression. But now this time, instead of us using 20 and 5 degrees Celsius, because we're doing it for the whole system, we'll use the most extreme values we have. So we'll work with the 27 and then the 0. Is that okay? So we can see over here, we are using the 27 and then the 0. And I can make my SGen the subject, and then I'll get it to be 0.341 watts per Kelvin. So you can try it out later on. I'll send you the slides and I'll send you the solutions as well, and you can try it out. And if you get stuck anywhere, you can just reach out to us and then we'll sort you out. Right. So yeah, I think that's it for okay. Please your question. You can unmute yourself and ask the question. Why the 27 and the 0? Okay. So you realize that if you look at the question first said determine the rate of entropy generation in the wall. And we know that entropy, we are going to be working with the heat transfer. That's the Q over the T. So even considering just the wall, I'm going to consider the temperatures at the surfaces of the wall. But the next part of the question said the total entropy generation associated with this heat transfer process. The heat transfer is not just happening across the wall. It's happening from the outdoor through the air there to the wall, then through the wall, and then to the indoor. Right. So because we are working from outdoor all the way to indoor, the energy or the heat transfer is coming from the point of 27 degrees Celsius to the point of 0 degrees Celsius. If we consider just the wall, then we can use 20 and 5. But if we are considering the entire system, then we have to use 27 and then 0. That doesn't make sense. So if you even look at it, the entropy generated in the wall alone, right, is 0.19. But entropy generated for everything is 0.34. That means that the entropy generated in just the air, right, just the air in and out will be the difference between them. Okay, that's good. So we can go back to the slide. I don't know if I start this one. I don't know if I'll finish on time. So what we'll do is that we'll continue from here tomorrow, and we'll be ending thermodynamics. What we'll be doing for thermodynamics tomorrow. So we'll be finishing up with this slide, and then we'll be done, right? So you have some assignments to try out. And please, if you have any questions, please feel free to ask. Okay, I'll send you the materials right away, and then I would also send you other things you can try your hands on as well, right? So before we end, are there any questions? Please, are there any questions? Okay, I'm sending the attendance link, so please do well to fill it. If there are no questions, then I'll stop the recording now.